So now let's come to the definition of pseudo random generator and what we mean by the hardness parameter. Okay. So let phi be a function from 0 1 to the power k to 0 1 to the power n or n greater than k. We say that phi is m hard pseudo random generator, so also will refer to this as PRG, if probability that f of x equal to 1 minus the probability that f phi of y equal to 1 is less than or equal to 1 over n for all Boolean functions f computable by circuit size at most n. Okay. So where this probability is over the choice of x, so here I choose x uniformly at random from 0 1 to the power n, and here I choose y uniformly at random from 0 1 to the power k. Okay. So let's understand this definition. What it is saying is that, well, phi is a pseudo random generator if basically here I am sampling x from the uniform distribution. So x is sampled from 0 1 to the power n uniformly. So the function f, so if I have, let's say, a function that is not too difficult, okay, so suppose if I have a efficient Boolean function, in other words, think of m as some polynomial. So if the function f is not able to distinguish between a string that is chosen from the uniform distribution versus a string that is generated by the function phi from the distribution 0 1 to the power k. Okay, and typically this k is smaller than n. Okay, so k has to be smaller than n. Okay, so for example, in this theorem we have n as 2k. Okay, I have k and 2k over here. Okay, so if you think in terms of k and 2k, what this is saying is that, well, if I take a string of length k from the uniform distribution and if I apply this function phi, it will produce a string of length 2k. Now that string versus a string of length 2k that is chosen uniformly at random is not able to distinguish between the output of this function most of the times, okay, for a very large I mean for a very large fraction of the inputs. And the important thing over here is that, so this has to be true for all functions that are efficient. So any efficient function is not able to distinguish between the two. Okay. Now what is the hardness parameter? So here H phi is basically this parameter m that we have. Okay. So this is the hardness parameter. Okay. Now Now, what we actually need, so what this is saying is that, well, I have a pseudorandom, so a pseudorandom generator is basically a function which is generating a string. Okay. Now, what I actually need is not just a pseudorandom generator, but a pseudorandom function generator. Okay. So, basically what I need is that some way to generate a function which is sufficiently which looks actually random to any efficient algorithm. Okay, so suppose if I take a random function versus a function that is generated by this pseudorandom function generator, an efficient algorithm cannot distinguish between these two. Here I am generating a string. Now I will move to functions. Okay, so do it here. Okay, so how do we generate a pseudorandom function? Okay. So let phi be, so we will use the parameter that Razborov and Rudich uses. So let phi be a function from 0 1 to the power k to 0 1 to the power 2k, and this is some pseudorandom generator. And yeah, so how do we generate the function? So what we can think of is that we can think of, so we'll generate the function as follows. So we will split the output of phi as phi 0 phi 1. Okay, we'll split the output of phi into two parts. Note that the output of phi is a string of length 2k. We'll divide it into two parts, where phi 0 is the first k bits and phi 1 is the next k bits of the output of phi. Okay, so now for a string x belonging to 0 1 to the power n, define phi x to be the function from 0 1 to the power k to 0 1 to the power k formed by taking composition of phi 0 and phi 1 based on x. Okay, in other words, so that is, so suppose x is the string x1, x2 up to xn, then phi of x will be phi xn composed with phi x n minus 1 and so on, composed with phi x1. Okay. So you take a string in 0 1 to the power k. Okay, so take a y. Okay, and now to that y you look at the first bit of x, x1, and depending on whether if x1 is 0 or 1, you apply phi 0 or phi 1. Now you have another string phi x1 of y. Now you look at the next bit and then you apply phi of x2 and so on, you apply phi xn. So ultimately what you get is a string in 0 1 to the power k, and that is what we refer to as phi x. So in fact this is actually the most crucial part of the proof. Okay, so this definition, and using this definition we will state a lemma, and yeah, we'll see why that is the most crucial part of the proof. So now we will what else do I have? Okay, so let psi of x comma y be the first bit of phi x on y. Okay, so this psi xy is a function that takes a n bit string, a k bit string, and produces a single bit. Okay, the first bit. And now what we will do is that, so here what we were doing is our input was y and it was indexed by x. Now we will flip this idea. We will index it using y and the input will be x. Okay, so define chi of y as a function from 0 1 to the power n to 0 1 such that chi y of x is equal to chi xy. Okay. So what have we produced now? So using this we have actually produced a function from 0 1 to the power n to 0 1. Okay, and yeah, we can view chi y as a distribution on functions from 0 1 to the power n to 0 1. Okay, so chi y is now a distribution. Okay, so what I said initially is that, if you recall, so we want to come up with a pseudo random function generator. Okay, and this is the distribution which is producing. Okay, so suppose if I randomly pick a string y in 0 1 to the power k, that will give me a function from 0 1 to the power n to 0 1. Okay. And okay, so the first property is that this is a distribution on functions. The second property is that any function in this distribution is actually efficiently computable from the phi's. Okay, so if k is polynomial in n, if k is some polynomial quantity, then phi y is computable by polysized circuits from psi. Okay, because how is chi y formed? So suppose if you have let's say that you have circuit for phi. Now what I will do is that I will break that output into two parts. I will look at my input now, which is x, and I will look at the bits of that input, and using if that bit is 0 or using whether that bit is 1, I will keep on building this circuit for chi y using phi 0 and phi 1. And of course I am using the fact that k is polynomially bounded, because I do this well, I mean this y that we have is polynomially bounded. I mean if k is not polynomially bounded, then so basically phi has to be polynomial in the size of n now. That is why k has to be polynomial in n as well. Okay, so any questions at this point? So now we will state a result by result from an earlier paper by Goldwasser, Goldreich and Micali, who essentially showed that, well, if you, so actually this distribution that we built right now, actually this distribution was from this paper. Okay, so this was by so what is the order of the authors? I have it over here, but Goldreich, Goldwasser and Micali in I don't remember the year now, but this was also I think from late 80s, 88 or maybe 86 also. So yeah, I'll just leave the year, but this was late 80s. So essentially this distribution was defined in this paper, and what they showed is that, well, if one can distinguish between these two distributions, so one can distinguish between the uniform distribution which is generating a function versus this distribution that is generating a function, then it would kind of break, it would kind of show that h phi is less than 2 to the power k to the power epsilon. In other words, it would kind of show that efficient pseudo-random generators, well, so what I mean over here, it kind of shows that it is easy to break pseudo-random generator. Okay. So if one can distinguish between these two functions, and as that is hard, as that by what we discussed earlier, therefore what it implies is that it is hard to distinguish between a truly random function and a function that is generated by this distribution. So let me state the result, and it will be clear. So let f be a function from 0 1 to the power n to 0 1, and be a uniformly random function, let g from 0 1 to the power n to 0 1 be a function chosen from the distribution phi y for a random y in 0 1 to the power k, then if there exists a polytime algorithm A such that A of f equal to 1 minus the probability that A of g equal to 1 is greater than 2 to the power minus order n, then h phi is at most 2 to the power k to the power epsilon for all epsilon greater than 0. Okay. So let's understand this. Again, what it is saying is that if I take a random function versus a function that is generated by this distribution, and if there is an efficient algorithm that is actually able to distinguish between these two, so by distinguish it means that the probability, the difference between these two probabilities is greater than 2 to the power order n, so by some significantly large probability, then h phi is actually easy. Okay, so h phi is bounded by 2 to the power k to the power epsilon for any epsilon, no matter what epsilon you choose. For any epsilon you can show it is smaller than that. Okay, so in other words, because this is not believed to be true, this conclusion, therefore what it means is that there is no efficient algorithm that is actually able to distinguish between these two. That is, the distribution that they created is actually as good as a uniform distribution for a polynomial time algorithm. Okay, because a polynomial time algorithm is usually limited in its computational power, so it cannot distinguish between a random function and a function that is generated. Okay, hardness of q, phi.
Hardness of phi is assumed that is less than this to the power to the power.
No, so what it is saying is that if so, if let's say if f and g are distinguishable by a polytime algorithm, then the hardness of phi is less. That is what it is saying.
And this conclusion is not believed.
This conclusion is not believed, because if this happens, then as I said, that you can actually break cryptographic protocols and various other things. I mean, it kind of implies that one-way functions do not exist. Hard one-way functions are easy to invert as well. I mean, hard functions are easy to invert as well. Okay. Okay. So now let me give the proof of Razborov and Rudich's result. And so the proof of this lemma we will see next time, okay, because this is the crucial ingredient. Using this lemma, we will see a proof of Razborov and Rudich's theorem today, and it's actually pretty easy. So recall what the theorem was. So the theorem said that there is no natural proof that separates NP from P slash poly unless this happens. Okay. So for the sake of contradiction, we'll assume that suppose there exists a natural proof. Okay. Suppose there exists a natural proof using a natural property, say P. Okay. So suppose there exists one. Now P is a natural property. What does it mean? So first of all, it means that okay, we'll use largeness. So probability that if I choose a random function f, P of f is equal to 1 is how much? What is the largeness definition of a natural property? 2 to the power minus O of n, right? So for that many fraction, for that fraction we know that it is it evaluates to 1. Next what we have is okay, so by constructivity P is computable in polynomial time of its input. Okay, therefore or P is computable in polynomial time. And thirdly, by the usefulness property, so if G is chosen randomly from the distribution phi y for y belonging to 0 1 to the power k, then so let me just give a name over here, computable in polytime by an algorithm say A. Okay, so if I take a G from this distribution psi y, then the probability that A of f outputs 1 minus okay, the probability that A of G outputs 1 is how much? Okay, so let's try to understand this. So what is this function G? What is P of G? Or in other words, does G satisfy this property or not? So G is chosen from this distribution we also argued that this distribution, any function that is chosen in this distribution is computable in polytime. Okay. So in other words, what this implies over here is that G belongs to P/poly. And if you look at the statement of Razborov-Rudich, it says that phi is a function in P/poly. Okay. So it says in the statement itself that for a function phi in P/poly. So therefore G belongs to P/poly. If G belongs to P/poly, what can we say about P of G? P is the property. So P of G should be what? 0 or 1? Huh? So P is a property that is P/poly useful. Okay. So by the assumption, we assume that there is a natural proof using this natural property. In other words, it should be able to separate a function which is in P/poly versus a function which is not in P/poly. Okay. So we start with a function that is not in P/poly, which has 1. G belongs to P/poly, therefore it should not have that property, right? So therefore P of G is 0. Okay. So this algorithm that we have now, which is actually able to determine this property. So probability A of f is equal to 1 is greater than or equal to 2 to the power order n. What is the probability that A of G is equal to 0? So this will always be 0. Okay. Because G, this algorithm will always output 0 on this function G, right? Because G does not belong to P/poly. P of G is equal to 0, right? So therefore probability AG, so this thing is actually equal to 0. So therefore this probability is also greater than 2 to the power minus order n. Okay, because the left hand side here is greater than or equal to 2 to the power minus order n, right? And that's it. So now directly we can apply the hypothesis. It satisfies the hypothesis of this lemma. So by this GGM lemma, what do we have? So we have a function that is chosen randomly. We have a function G that is chosen from this distribution psi y. Okay. There is a polynomial time algorithm that is able to distinguish between them. Now, if there is a polynomial time algorithm, which we know is able to distinguish between them with probability at least so much, then we know that h of phi is bounded by this. Okay. Therefore, by this GGM lemma, h phi is less than 2 to the power k to the power. What did we have it as? Small o of 1, I think, in the statement. Epsilon, right? In the Razborov-Rudich's theorem. Okay. 2 to the power k to the power epsilon for any epsilon. Okay. So this proves the theorem. So now as you can see that essentially the crux of this theorem is in this lemma. So if we can actually prove this lemma, then it completes the whole picture. Okay. So as I said in the beginning that the major part of this paper was not the actual result. The result is not very difficult, but to form the intuition as to what is a natural proof and why does natural proofs not suffice. Okay. So they had to come up with this intuition for largeness, the intuition for constructivity, and of course usefulness is something that has to be there. That it is a property that is actually separating a function from a class. But these things, and they argue why it is true. And now it should not be just some abstract property. Okay, it has to be something which is true for any of the proofs that were shown earlier. Okay. So a majority of their paper actually is devoted to showing that various proofs, all these, in fact not various, but all the circuit lower bound proofs, the major circuit lower bound proofs, that were shown till that point were all actually natural proofs. Okay, so that is why it makes it so interesting. Okay.
GC and lemma, what is this phi? Like this is for all phi.
No, so this is
So in the earlier point there is no phi. So at the end when we are going to replace phi with for all pseudo-random generators phi. Because in the RazborovRudich theorem you have written that for every pseudo-random generator phi.
yeah. So this is for any pseudo. So you fix any pseudo-random, you take any pseudo-random generator phi. Okay. Now, yeah, so I should have said it somewhere over here that you take any pseudo-random generator phi, because only when you take a pseudo-random generator phi, you will be able to construct this distribution psi y. It corresponds to phi. Now, once you have that, then this follows. Yeah. Okay. So next time we'll complete the proof of this lemma.
This psi y is coming from some pseudo-random.
Psi y is coming from this construction exactly. So it is exactly this construction. And now where it so what does it say over here that well, y is chosen over here. Now why does G belong to P slash poly? Because this phi that we have, if you look at again the statement, phi is in P slash poly, and now from phi we argued that psi y can actually be constructed by polynomial size circuits. Okay, so therefore psi y is constructible by polynomial size circuit, which puts G in P slash poly, and therefore P of G is equal to 0. So therefore the algorithm that we have for P will always output 0 on G. So the probability that it is equal to 1 is 0.